All right. Now we're going to talk about capacitance, which is one of the two ways energy can be stored in a circuit component. So we're going to talk about energy storage in electric fields, and that is accomplished using devices called capacitors, which we're slightly familiar with already. So we define a capacitor as just a system of two separated conductors that hold the same charge. We can separate spheres, we can separate cylinders, we can separate plates. This is the main one we'll look at. Or there's even more distributions, but we're just going to cover these three as our main cases of capacitance. So, by definition, capacitance defines how efficient your device is at storing charge for a given potential difference. So, if you have a higher capacitance, that means you can store more charge for a given voltage. And our units of capacitance, if we work it out, are going to be coulombs per volt. And we define that as a farad, like Faraday. So, since this potential difference delta V depends on Q, because electric fields depend on Q, uh, that means that Q will always divide out of capacitance. So we define this quantity C because it's independent of your charge stored. So it turns out the only way to affect capacitance is to change the geometry. So it does not matter how much charge is stored. So our recipe for finding capacitance is first find the E field between the conductors, probably using Gauss, then integrate between the two. And of course, we ignore all signs because we're just interested in the absolute value. And then we just plug in using C is Q divided by delta V. Make sure that you get no charge quantity in your capacitance because it can't show up. It has to be only geometry, so things like length, radius, and of course, some epsilon knots are the only thing that'll show up. All right. So the first case we'll look at is the spherical capacitor. So we have two conducting spheres. So we have a conducting sphere in the center with positive charge, and then we have some spherical shell with equal negative charge on the outside. So first, actually, without performing any derivations, we can determine the behavior of this field. So by definition, these capacitors are conductors. So what that means is that we can definitely be sure that E is equal to 0 inside this conductor. So from 0 to R1, we know that we're going to get a nice constant 0 electric field. So E is equal to 0. And we know this is true because we are in a conductor. Then, as soon as we're outside, well, again, Shell theorem just says it looks like a point charge. So if we look at our field lines, we'll get something like this, right? The field is going to fill this space between the cavity. And using the source to sink rule or the downhill pointing rule, we see that we get a nice radially symmetric E field. And I'm drawing this because we're going to have to use Gauss's law soon. So we get a nice inverse square law. And then, once we reach the conductor, if this shell has any thickness, the E field would be 0 inside the shell. But outside the distribution, we can use Shell theorem again. And since the net charge of this system is 0, if I'm outside the system, like at this point right here, it looks like a Q and minus Q stacked on top of each other, which is, of course, nothing. So outside of a capacitor system, you'll see it's generally true that we get E equals 0 for a different reason. So E equals 0 at the ends for different reasons. So E equals 0 in the first region because we're in a conductor, but E equals 0 on the outside because there's no net charge enclosed. And again, to justify this one, we know it just looks like a point charge, K Q over R squared. So we have 0, inverse square law, and 0. Starting from Gauss, derive an expression for the E field between the spheres. So I say starting from Gauss's law, so we are actually going to have to use Gauss's law. We do know what it is, right? My graph says it's this. So again, let's verify the Shell theorem basically is what we're going to do. So we can draw ourselves a nice little Gaussian surface, and it's going to be a sphere because we have spheres in this case. And we can see that my field lines are perfectly penetrating the sphere. So we can, of course, write that the electric flux through my Gaussian sphere is the enclosed charge divided by epsilon naught. And since I chose a sphere that gets perfectly penetrated by all the field lines, an area of 4 pi r squared is getting pierced, and that's a little r. And what is my Q enclosed? Well, it's just capital Q. So we see that there's no variable on the right side because we're not enclosing any extra charge as we go further, which means we can just write E as the usual 1 over 4 pi epsilon naught times Q divided by r squared. As expected, right? We get our point charge formula. K Q over r squared. Derive an expression for the absolute value of the potential difference between the two spheres. Well, potential difference, we said E points downhill. So if you add up all of your downhill contributions, you figure out how far downhill you actually went. So we said that the E field is going to be 1 over 4 pi epsilon naught times Q over r squared. And for our integration limits, our field begins at the inner sphere and ends at the outer sphere. So we integrate from R1 to R2. Lots of these things are constant, right? Q is a constant, and so is 4 pi epsilon naught. So now we just have a relatively simple integral to do. So we should be a bit careful with this. This is natural log, right? Because we have r squared on the bottom. So it actually is negative 1 over r. So we get negative Q over 4 pi epsilon naught times negative 1 over r, evaluated from R1 to R2. And if we work that out and we make it non-negative, if we plug in 1 over R2, that's going to be a small number. And if we plug in 1 over R1, it's going to be a bigger number. So we'll write it like this. We know it's going to be Q over 4 pi epsilon naught 1 over R1 minus 1 over R2 is going to be the absolute value. All I did is I just took away the signs to make it a positive quantity. Because again, 1 over R1, since we're dividing by a bigger number, that's going to be bigger than 1 over R2. So now we can derive an expression for capacitance. So capacitance, by definition, is the charge stored on one of the conductors divided by the absolute value of the potential difference between them. And that allows us to write Q divided by this potential difference, Q over 4 pi epsilon naught times 1 over R1 minus 1 over R2. And we do know that that Q needs to cancel out because Q is not a geometry factor. Q is not geometry. So good thing Q divides out. And my 4 pi epsilon naught goes up to the top. So I can write C is equal to 4 pi epsilon naught times 1, or divided by 1 over R1 minus 1 over R2. We could simplify further if you'd like, but I'd like to leave it like that. So notice that R1 and R2 are the sphere radii. Those are geometric factors, and the rest of the stuff is constant. So that's a sphere. Now we're going to have cylindrical. So two concentric metal cylinders have equal and opposite charges plus Q. And we give their radii. So we can still use Gauss's law, because since our cylinders are conducting, this means that we know that the E field points perpendicular to the surface of these conductors. So we know the E field starts out perpendicular. And we'd get something roughly like this. So as long as your separation distance is small, we can approximate this as a uniform electric field direction in this region. And we can see this is our nice cylindrical symmetry case. So let's do that. Derive an expression for the capacitance of the system. So same idea. First thing is we got to get E. So if we got to get E, of course that means we're going to draw ourselves a Gaussian surface. So of course it's a cylinder in this case. Now I can write the integral of E perp dA, which is flux, is equal to my enclosed charge divided by epsilon naught. And I'm not necessarily enclosing the whole cylinder. So instead of calling it X, maybe let's call this distance X instead of L. So what we can do to find Q enclosed, since it's uniformly distributed, we can define this quantity lambda as charge per length. Because that will be the same, so we can just multiply lambda by our enclosed length to get charge. So this is the cylinder. The flux pierces the entirety of the barrel. So the barrel of the cylinder is 2 pi r, and it's extended for a distance x. And then my Q enclosed is going to be lambda times the length enclosed divided by epsilon naught. So we get our usual E from a line charge expression of E is equal to lambda divided by 2 pi epsilon naught times 1 over r. Which is not what we want. We want the capacitance, but this is the first step. So also realize that another Gaussian surface that works because of the approximations we made is you could have instead just enclosed the entire length of the cylinder, and you could have made this length L, and you could have made this quantity Q, and you get the same results. So that would have worked too. All right, so now we'll do the usual. Delta V is the negative of the integral of E dr, and we're integrating from R1 to R2 again. And we have a new E field expression. So we can factor out a whole bunch of stuff again. So we get negative lambda over 2 pi epsilon naught times the integral from R1 to R2 of dr over r. And that one is special because that's going to be natural log. So that evaluates to ln of r2 over r1, because if we evaluated this, we'd get ln r2 minus ln r1, which of course we can simplify using the division rule of logs. So we get that as our potential difference. So of course we'll take an absolute value when we plug in. So capacitance is defined as the total charge on one of the conductors divided by the absolute value of the potential difference. Then our Q, our total Q, can be written as lambda times L, or you could have substituted away for lambda, it doesn't matter. I'll substitute away for Q since I already have my V in terms of lambda. So Q is lambda times L, and the absolute value of the potential difference is just our expression from above without any negative sign. So notice what cancels and what doesn't. Lambda is not geometry, right? I can choose whatever lambda I want on a conductor. So it makes sense that lambda should cancel. The 2 pi epsilon naught comes on top. And then I'm dividing by the ratio, by the natural log of the ratio of the radii. So once again, it makes sense. It is following the same form as last time. It's just we have a different field functional dependence. We have a different denominator function here. So that's the coaxial cable. Oh, no, I missed an L. This does depend on L. I did not forget. So it is a geometric factor. So it should make sense that the capacitance of this system does depend on this quantity L. Because if my cylinders are really long, of course, there's a lot of space for them to store charge. between the two, right? That increases your volume that your E field can exist in. So it makes sense that this capacitance has a factor of L involved to it. So sometimes we'll find not the capacitance, but the capacitance per unit length. And we're ending actually with the easiest case, and that's the parallel plate capacitor. So to begin, we're going to try to remember what this field looked like. We did this in the Gauss's law section. So remember, the field from a plate is uniform. And we thought about that with the vision cone, right? If you get farther above a circular plate, you're seeing more of it in your effective vision, and you see more area at the same rate that the field is falling because of the quadratic dependence. So first, again, using our sources and sinks rule, we know that the field from the positive plate is going to point directly away from the positive plate at all points. And of course, because of the sink rule, we know that the field is always going to point towards the negative plate. So since this field is uniform, we know all of these vectors are going to be the same length. So above the top plate, we see that E equals 0. And below the bottom plate, E also equals 0. But between the two plates of the capacitor, we see the fields don't subtract, but instead they add. So between the two plates, E is 2 times E of one plate, which is uniform. So describe the capacitor field. Well, capacitor field is 0 on the outsides, and it's double the field from one plate on the inside and uniform. So starting from Gauss's law, let's derive an expression for the E field between the plates. So again, we want to think about this as a large plane of charge. So we're just going to derive E from one plane first, and then of course double it. So think about having a large plate, and we'll draw ourselves a Gaussian surface. Some people pick the pillbox shape. I like to just keep it as a cylinder. And it's going to enclose some little charge in here. And we'll say this is the positive plate, which means the electric field is going to perfectly pierce the caps of the cylinder like that. So Gauss says that the integral of E perp dA is equal to Q enclosed divided by epsilon naught. And then I believe we reserved the quantity A for like the entire plate area. So we're going to call this some different area as our cross-sectional area. We'll call this A2, I guess. So we have an E field E, and it's penetrating 2 copies of this area A2. And what is our Q enclosed? Well, for the same time last time that we did with the coaxial cable and linear charge density, this is an area charge, so we can define sigma as the total Q divided by the total area. So this means that Q is just going to be sigma times A. So my Q enclosed is sigma times this quantity A2. And now we see we get some simplification. So you see that E from one plate is sigma over 2 epsilon naught, which is, of course, our usual expression. But we actually want the field between the two plates, so we got to make sure we double this, right? Because the negative plate is also contributing that. So my net E field is going to be 2. It's going to be 2 times E from one plate, which is equal to just sigma over epsilon naught, because we've deleted that factor of 2. And then sigma actually wasn't a variable in our problem, so we have to write that as Q divided by A. And this is the real Q in the real area. All right, but the potential difference is really easy because we said that E is constant constant. So this means that this delta V, which is the absolute value of the integral of EdR, well, if we just have the same field strength E everywhere, well, you just do our simplification from our second unit that we said delta V is equal to E times D if the field is constant, which in this case it is. So delta V is equal to ED. So I just attach a factor of D to my E field expression. I get QD over A epsilon naught. Because I have a field of Q over A epsilon naught for a distance D. Drive an expression for the capacitance of the system. We know the drill by now. Capacitance is the amount of charge you can store per unit of potential difference. Q is Q, and delta V is QD over A epsilon naught. So this means we get C from two parallel plates, which is a formula sheet equation that's used all the time. We see we get an epsilon naught on top, we get an A on top, and the D stays on bottom, and Q, of course, cancels. So those are our three cases of capacitance that we need to know how to derive. So we had the sphere, we had the cylinder, and we had the parallel plate. So now we're actually going to go more into detail on properties of parallel plate capacitors specifically. So we see that there's some geometric factors in the capacitance formula. Of course, it's the area and the plate separation D, but also epsilon naught is involved. So epsilon 0, which we've always used as epsilon 0, is the electric permittivity in a region of space. And we've always assumed there's nothing in this region that's affecting the ability of a material to polarize. But we know that insulators do actually polarize. So if you insert an insulator between the plates of a capacitor, you'll get polarization that happens. And that polarization, as we saw when we looked at these properties back in Unit 2, it causes a lower field strength because all of these polarized molecules are going to generate a small E field that fights the original E field between the plates. So effectively, inserting this dielectric material, which we'll call it, lowers the overall E field. And again, we know the charge is going to stay the same because we're considering capacitors that are isolated. So if you just charge a capacitor and then put this dielectric material through it, the charge is going to stay the same because the charge can't go anywhere because there's no way to move through an insulator. So what this means is that you're going to have a lower potential difference because you have a weaker E over the same distance D. So capacitance increases. So this is another way to increase capacitance, is instead of changing the geometry of the setup by actually changing lengths and areas, you change the geometry by putting a material between the plates. So we define this constant kappa as the factor that you shrink the E field by inserting a dielectric material in an isolated capacitor. So if you put a material between the plates and the field strength is halved, kappa would be 2. And we've ignored this up to this point because the kappa value for air is 1.006. So that's basically 1. So if you have a vacuum, kappa is 1. And that's a hard lower limit on kappa because if the field always getting reduced, you can't actually reduce it to a value higher than its original. So kappa is anything from 1 to double or triple digit numbers in certain materials. Most of them are single digit though. So the real parallel plate capacitance formula incorporates this value of kappa in front as a prefactor, because essentially what it's doing is it's changing your permittivity, which is again how susceptible your material is for polarizing, from epsilon naught to kappa times epsilon naught. So we can also think of this as just affecting the permittivity and saying epsilon is equal to kappa times epsilon naught. So maybe if instead of including a kappa, you could write this as epsilon A over D, the formula. But I think it's a lot more understandable if we see the kappa in front. So now we'll do a quick proportional reasoning. So we have all these different parallel plate capacitors. We got their area, we got their plate separation, and we got their dielectric constant. So we can see that 2 of these are air-filled, 2 of these are not. So of course, if we're ranking capacitance, we should probably know the formula for capacitance. Capacitance is kappa epsilon naught A over D. So that means that capacitance is proportional to capacitance, or to kappa, the dielectric constant, on the numerator, area on the numerator, and the plate separation D on the denominator. So let's just work that out. So this is pretty straightforward to kind of work out for each of these. And again, I wouldn't really like plug in all the letters. I would just reason through everything. So if we were to go through, we can do our technique of inserting numbers to represent the values of each quantity, and then we'll compare. So C1, we have a plate area of A, plate separation of D, dielectric constant of 1. So C1 in this scale is going to be 1 for kappa, 1 for area, 1 for dielectric. So we get an effective value of 1. Now for C2, we doubled everything. So for C2, we doubled everything. So that gives us an effective capacitance of 2 in this unit system. For C3, we halved the area, we halved the separation, but we quadrupled the dielectric constant. So that's going to be an effective value of 4, right? Because area and separation are inversely related. So if I did the same thing to both of those, they effectively cancel. So I'm just looking at the effect of the dielectric constant, making that 4. C4, I double the plate separation, and that's all I did. So this gives us an effective value of 1/2. And then for C5, all I did is I doubled the dielectric constant. That also gives an effective value of 2. So now by reasoning through it, we can just construct our ranking. So we see the lowest capacitance on my list is 1/2, which was, all that was doing was doubling the plate separation without increasing anything else. So C4 is the least. Then the only capacitance that was working out to be 1 was actually C1. Then we see C2 and C5 high. And then we have C3, which was our lone value of 4. So again, when we looked at our effective capacitances, U were 1/2 for C4, C1 was 1, C2 and C5 were 4, and, 2, and C3 was 4, as we saw from our list. Of course, you could have done this a lot faster than I did, but I was just showing that. All right. A group of students are performing an experiment to determine the dielectric constant of a material. So this is a very classic lab to know how to do. So we have 2 parallel plates that are conducting. So I'm just using foil. And they have different amounts of this ceramic material between the plates. And we're changing the plate separation, making sure it's fully filled with this dielectric each time, and we record the capacitance. So we see that our variables are D and C. Well, of course, we do have a formula that relates capacitance and plate separation, right? Capacitance is kappa epsilon naught A divided by D. So our variables were C and D. So it doesn't look like I have to transform anything for C. C is just C. But D is on the denominator, so remember we can write this as everything times 1 over D. So instead, I can write all of my constants in front, and then I can factor out a 1 over D. So this is, of course, not the only linearization you could do, but I'm graphing the capacitance on the vertical axis and 1 over D on the horizontal, because you got to make it linear. So I had to include that inverse relationship. And of course, we're going to need it later. We know that our slope is equal to kappa epsilon naught times A. And it did give us the plate area was 10 to the minus 2. So all we need is the slope to solve, because kappa is given by slope divided by area times epsilon naught, which we know area, and we of course know epsilon naught. All right, and you know that I will never graph on camera, so we did our usual off-camera mining to get our capacitance versus 1 over D graph, and we see it's pretty good, pretty linear. We just have to be careful of this 10 to the minus 12 scaling on C. And Desmos gave me this as a regression equation. So we see the relevant quantity as our slope. And we wanted this fact that slope was equal to kappa epsilon naught A, which means that kappa is equal to slope divided by epsilon naught times A. And the slope is 6.88 times 10 to the minus 12. Epsilon naught is the usual value of 8.85 times 10 to the minus 12. And area was just 10 to the minus 2. So we can see that our dielectric constant is going to have units of nothing. Well, I guess we can't see that easily. You could work it out and see that if you know the units of epsilon naught. What I meant to say is we can see that our kappa value is going to be on the order of 10 to the 2 or 10 to the 1, depending on this. So it's going to be close to 100. If we work it out, it's roughly 78. And that is very large for a dielectric constant for usual things, but I picked this special ceramic material that's specially designed for capacitors. If you use something like paper, it's going to be in the single digits. But this is a standard capacitance lab to know how to do. And it's pretty easy to do it in person also. You just need one of these special capacitance meters, which works like a voltmeter. So I've alluded to the fact that these capacitors store energy in the electric field. And depending on what two of the capacitor quantities you know, you can use one of these 3 formulas to find the stored energy. So again, the energy is stored in the field between the plates. And the field is determined by the charge, which determines the potential difference and all that. So again, the energy is stored in the field between the plates. There is a formula we can actually derive for the energy density, but we're just going to use this. So I would take this more or less to be the definition, because we said that energy is QV, and we pick up this 1/2, which we're going to prove. And then if you do some substituting, which we'll also prove, you can get these other 2 formulas. So remember, we have the definition that capacitance is Q over delta V. So this means we can always replace any of these quantities with the other 2. So this solves it for all 3, right? So if I want to replace one of these, we see this formula doesn't have capacitance, this one doesn't have charge, and this one doesn't have potential difference. So we can always substitute one of these away. So we're going to argue this. So of course, from electrostatics, we said that delta V is the energy per charge. So delta U should be the total charge times the potential difference. But we see with the capacitor formulas, there's this factor of 1/2 that shows up. So we're going to justify this. So why is the total energy required to actually store this, why is this actually less than Q times epsilon? Well, we'll say split this into two different cases. So first, let's look at when the capacitor is uncharged. So if the capacitor is uncharged, and I have to move a charge across this gap, how much energy does it take? Well, my delta U is going to be, we'll use D notation because we're going to use calculus. We'll say that a little change in energy is going to be equal to whatever my test charge is, dq, times the V between the plates. But if my plates aren't charged, there's no delta V. And we'll call this a delta. Which is equal to 0, because there's no potential difference. So it doesn't require any energy for me to push the first bundle of charge across the capacitor. But what about when my capacitor is fully charged? Well, when my capacitor is fully charged, we see that now, if it's fully charged, and this is not actually how we move charge, by the way. It doesn't actually cross the gap. It sort of moves around the circuit. But for sake of example, we'll just pretend we're moving it across this gradient. And we actually know if it's fully charged, it's at its maximum potential difference, which we set as epsilon. So here, we see that du, in this case, is my bundle of charge dq times delta V once again, which is going to be dq times epsilon. So we can see our total potential energy isn't going to be the total charge times epsilon, because that's only the amount of energy it would take if I had to push the whole charge across the potential difference. But that potential difference isn't epsilon the whole time. It's slowly building up as I push more charge between the plates. So we actually know that it's going to be somewhere between 0 and Q times epsilon is going to be our value as how much energy is stored in the capacitor. Because it takes me 0 energy to push the first bundle, but it takes me dq times epsilon to push the final bundle of charge. And since none of those cases are there for the whole time, we know it's going to be somewhere between there. And actually, since capacitance is linear, it's the exact midpoint. So let's show that. Sketch a graph of the potential difference across the capacitor as a function of stored charge. So we need an equation with Q and V. Well, we have one, because capacitance is defined as Q over delta V. So this means my charge on the capacitor at a given time is C times delta V, which means that delta V at a given time is Q over C. And what do we notice? That is linear. So if I have twice as much charge on the capacitor, my potential difference across the capacitor is doubled. So this means that we can make ourselves a nice line, because I start with no charge and I end with a charge Q. And if we actually cared about this, which we could use to get a different form of the equation, we actually know the slope is equal to 1 over C. So that actually gives us an alternate way of doing this. All right, so let's verify it. So we can probably guess based on the picture that there's some sort of calculus operation involved. And let's verify it. So we know that a tiny energy change would be whatever my current voltage across the capacitor is times the bundle of charge I'm moving. So my total energy is going to be my total amount of energy cost So I'm just integrating all of that up. And what is V? What is the integral of V with respect to Q? Well, you could actually create this function to get one form of it, but look at what we have. We're integrating a function which can be found as the area. So we actually just want this area. So we want this area, and it's a triangle. So 1/2 times the base, which is big Q, times the height, which is epsilon. So with minimal calculus, we've derived that it's exactly 1/2 Q times the max voltage. So we could have done this an alternate way. With instead of V, we could have substituted away in terms of C, but we're just going to show that once we have the formulas, it's quite easy. So verify the two alternate expressions. Well, we started with U is 1/2 Q times epsilon. So let's substitute away Q first, because we know that Q is equal to C delta V, which is equal to C times epsilon. And again, I'm just manipulating the capacitance definition for this. So I get 1/2 times C epsilon times epsilon, which is 1/2 C epsilon squared. Notice that looks similar to like a spring potential energy. That's not a coincidence. Or what if instead we started with 1/2 Q times epsilon. I wanted to actually get rid of this epsilon. Well, we know delta V can be written as Q over C. So we can replace that epsilon with Q over C. So we pick up an extra Q on top and a C on the bottom. So we get 1/2 times Q squared over C. So there are 3 different ways to get the energy. So it's kind of similar to resistor power in the effect where we have a definition, like power equals current times voltage, and then we have a relationship that says current and voltage are linear. In Ohm's law, we have a very similar situation here. So we get all these different formulas. So depending on what you know about your capacitor, or especially what's constant, helps us determine which one of these is the easiest to analyze. So lastly, we'll end with these factors of change questions, which is saying I do something to my capacitor. How does this change? So it's easiest to just start with what's directly changed and leverage some of these relationships. So definition of capacitance, or using that as the parallel plate formula helps. Usually Q equals CV is the more useful form here. Delta V is ED for a capacitor. And you can use one of your favorite energy formulas. So there are 2 cases here to determine what's constant. If your capacitor lives by itself in the middle of nowhere, the Q can't go anywhere. The Q can't just vanish, so it's constant. But if your capacitor is attached to a battery, no matter what, it forces the same delta V because of the loop rule. Because if this is forced to be of certain voltage, so is this. So we'll see it's true that anytime a capacitor is connected to the battery, it's going to be constant voltage. Just like when 2 things in parallel have the same volts, same idea, right? I'm connecting these in parallel, so it must have the same voltage. All right, let's do it. Capacitor is charged before being isolated. So that's actually the first thing we should see. Isolated. Isolated means I instantly know Q is constant. Then I double the distance between the plates. All right, so what can we do? Area obviously doesn't change. Distance doubles. Kappa, same. I didn't insert a dielectric or anything. Capacitance, that's not straightforward. We'll do that in a minute. Q, that's the constant one. Then we'll come back. U, E, and epsilon's going to be the same. So I started with the ones that I didn't have to use any formulas for, and I just sort of got for free. Because we didn't change the area, we doubled the distance, we didn't put a dielectric in, which means we're also not going to have a different permittivity, and the isolated capacitor means constant Q. All right, so let's start with capacitance, because that sort of unlocks a lot of things. So capacitance is equal to kappa epsilon naught A over D. So didn't change kappa, didn't change epsilon naught. Well, you're never going to change epsilon naught. You can change epsilon, but not epsilon naught. A is constant, but D was doubled. So this means that capacitance is halved. So I half the capacitance. All right, so now we got to get delta V. How do we get delta V? Well, we have the relationship that delta V is equal to Q over C. Q didn't change, capacitance got halved, which means that delta V doubles. And that should make sense, because the E field from the plates isn't going to change, but we've just stretched the plates to double their original distance. So that means our E field actually does stay the same too. We can reason that because we didn't change the charge density or anything, and we can use delta V equals ED. I think we'll actually just write that down here explicitly. So we also know that delta V is equal to ED. So if we doubled the voltage and doubled the distance, that means that our E field did not change. And then we can pick our favorite capacitance formula for U. I will probably pick Q squared over 2C because that's the one that involves the not changing thing. So I can say U is equal to Q squared over 2C. Q was unchanged, capacitance was halved, so my energy stored is doubled. And that should make sense, because this capacitor is not going to want to get separated because there's this electrostatic force. So if I somehow pull these plates apart, that costs me energy. That takes work. There's more field in this volume, so the energy had to go up. So that's the isolated case. And now, of course, you can guess that we are going to do the connected to a battery case. So again, see what's constant and just wrap and just do your analysis all around that. So Q is constant. I looked at what was directly changed and had to use all these relationships to figure out everything else. Okay, so now we have the case of a capacitor connected to a battery. So we have a capacitor that's connected to a battery, it's charged by the battery, remains connected, and then we insert a dielectric between the plates. So the fact that the battery remains connected tells us it's not the charge that's constant, but it is the voltage, delta V. So again, it's really important that we know that this is a different case, because it actually changes a lot of the energy analysis. So again, the isolated case was all about Q being constant because the charge couldn't change. There's nowhere for the charge to get dumped. But if we have a full circuit, of course the charge can change. But what the battery does is it forces a potential difference. So the battery's connected, and then we have a dielectric material inserted. So what we know directly is that the plates area don't change, the plate separation doesn't change, kappa is tripled, which means the permittivity is tripled. And then to begin our analysis, we know that it's connected to a battery, so voltage or potential difference is the same. All right, so now we can just pick our formulas to use. Usually it's important to start with capacitance, because that unlocks a lot of the other relationships. Capacitance is kappa epsilon naught A over D. We didn't change the area, we didn't change the plate separation, but we did triple the dielectric constant. So kappa got tripled, so this means we're going to have 3C. So the capacitance got tripled. And now for the Q, Well, if I have the same voltage, but triple the capacitance, that means I actually need 3 times the charge. And how do I know that? Well, we know it's linear, because we know that the charge Q is equal to C delta V. Same potential difference, triple the capacitance. So our charge also tripled. And now we can just do the energy and electric field. So maybe let's do the energy first. So for the energy, delta V is constant, so let's pick that one. So the formula that has delta V in it, I would just pick U is equal to 1/2 C delta V squared, because it involves the least plugging in. So delta V is the thing that's constant. So I'm squaring 1. And then we said our capacitance was tripled. So my new energy stored is just tripled. Okay, so interestingly enough, inserting this dielectric causes the energy to go up when we're connected to a battery. We'll see it's actually different if it's isolated, which is interesting to think about. But let's actually see why that is. So let's find the electric field. So the electric field between the plates, we know that we have the relationship delta V is ED. We didn't change delta V, nor did we change D. So what does that mean? Well, that means that none of the quantities there are actually going to change. So we actually get the same electric field strength. So how does that make sense? How does that make sense? That we actually have the same electric field strength between the plates, but triple the energy? If the energy is stored in the field? Well, if we think about it, we know the field has to stay the same in the parallel case, because V is ED. And even when you're inserting a dielectric, you're not changing D. So even though that would shrink the field in the case of an isolated capacitor, that's countered by the fact that by putting this dielectric in, you're sort of pulling more charge from the battery. So maybe we have like this in our original case, but as soon as we put in the dielectric, the field would normally be weaker. So in order to maintain that electric field, we actually need to pull more charge from the battery. But I still don't think that is accurately comparing why this stores more energy. Because energy is stored in the field. Well, if we think about it, in these dielectrics, energy goes into polarizing these quantities. So when we drew our little molecules, this polarization actually takes energy. So we do have the same field strength, but there's also this extra potential in this sort of polarized molecule case. So that's why it's actually triple the energy, even though the field is the same. And last, we have an isolated capacitor. It's charged. We disconnect the battery and remove a dielectric. So the first thing we should see here is that the battery is disconnected. Battery is disconnected. Notice I didn't say isolated capacitor. I said battery is disconnected. Well, if you have no battery, your capacitor is isolated. So Q is constant in this. This is another way of saying the Q doesn't change. Then we pull out the dielectric. So this does some weird stuff to some of our factors of change. But we'll see it's still really the same analysis. Okay, so what do we know? I did not change the plate area. I did not change the plate separation. I did change kappa. So my new dielectric constant is 1, right? Because air is kappa equals 1. So I essentially quartered my kappa. And you might be thinking that's an issue, because we said kappa must be strictly greater than or equal to 1. And again, we're just looking at the ratio here. So that's totally legal that we have a divide by 4 here, because we're saying that kappa got divided by 4. What is capacitance then? Well, capacitance, you can probably guess what it's going to look like at this point. Usually it helps to start with capacitance because that's kappa epsilon naught A over D. Kappa got quartered. Area didn't change. Plate separation didn't change. So we get a quarter of the capacitance. So capacitance got quartered. Q is constant. Because we have an isolated capacitor. And now what is delta V? Well, use your favorite flavor of Q equals CV for this because we know the other two. So we can say that delta V is Q over C. And we said the Q stayed the same, but the capacitance got quartered. So I'm dividing by a quarter, which means my new delta V is actually 4 times the original. So let's quickly diagnose why that makes sense. So why does it make sense that we're actually having 4 times the potential difference? Well, this is the case where our charge is the same. So in each of these cases, we have the same amount of charge on the capacitor plates. But we said that the field is weaker for the same charge in a dielectric material within the capacitor, because we have this sort of backwards field that's fighting the original capacitor field. So how is delta V? How is delta V 4 times? Well, this dielectric effectively quarters the vacuum field strength. So we have a quarter of the original strength. So it makes sense that E is actually going to quadruple. Because if we look at delta V is equal to ED again, we see that our new E field, well, let's see, same distance, but delta V got quadrupled. So we see that our new E field was also quadrupled. Now our permittivity, that relates to kappa, that's also a quarter. Because we see that it went from factor of 4, which was highly polarized, to kappa equals 1, which was our vacuum polarization. So we see that that was going to be quartered, just like kappa. These two quantities always match, because kappa tells you what epsilon naught turns into. And then pick our favorite energy formula. Usually it's Q squared over 2C is the good one to use here, because Q is constant. Q is constant, so I'm squaring 1. And then the capacitance got quartered, so I'm dividing by 4, or dividing by a quarter once again, which results in 4. So we see that my new energy stored is quadruple. So why does that make sense? Well, if we look at our picture, this one's more clear why energy goes up. So there's 2 ways of thinking about it. So first, notice the field is just getting stronger. We have the same charge, but a stronger field over here, because there's no dielectric weakening it. So the field is stronger in that area. But another way of thinking about it would just be to say, well, all of these charges in the dielectric, these molecules are going to be attracted to the plates. And you can't just remove attracted molecules for free. So it has to cost you some energy. So if you're spending energy to move that dielectric material out, because it's attracted, it must cause an increase of energy to the capacitor system. So, of course, you're never going to be asked to fill out all 9 of these things, but I think it's an interesting exercise to show all these different cases of capacitance. So that's kind of everything we have before we start putting these things in circuits.